order to get to the big takeaway, we are going to have to take 2 cold showers together. That is to say, we are going to have to address 2 sticking points that typically arise in this discussion. First cold shower. Most people are terrified of mathematics. For many of you, at some point, someone pointed a finger at you and told you that you weren't smart enough to understand it, or perhaps that you didn't need math in the real world, so you were fine not knowing it. Often that person was you. This is common, and it is false, and it will keep you from understanding the really cool story I'm about to tell you. So, for the duration of the talk, I'm going to need you to pretend that that conversation between you and yourself never happened. Second cold shower. Beauty is an ill-defined and oft-maligned word. As a matter of fact, great author Toni Morrison says that physical beauty is one of the concepts in the history of human thought. And so, instead of talking about beauty directly, I'm going to tell you a story. This is a story about infinity. So, if you start counting 1, 2, 3, 4, etc., you will never run out of numbers. You can count forever. But by a trick of language, mathematicians can talk about the set of all the counting numbers instead of having to list them all, which is nice. Mathematicians call this set the natural numbers and denote it with this special n. When we talk about the number of that, mathematicians use the word cardinality, which is just a fancy word for size. And the size of the natural numbers is aleph null. We're using this Hebrew letter instead of the usual sideways 8 for reasons that will become clear shortly. Well, infinity is a funny thing. Suppose I were to dump in all of my negative natural numbers and 0 into my original set. I would get what mathematicians call the integers, or the whole numbers, and we denote it with this special z. And it turns out that the size, the cardinality of the integers, is in fact also aleph null. And now you're thinking to yourself, well, this is absurd. I just added an infinite number of numbers into this set. Surely it must be a larger set. Well, when mathematicians compare sizes, what we do is we compare lists. So let's draw up some lists. On the left, I have the natural numbers, and on the right, I have the integers. And the way that we say that 2 infinite sets are of the same size, if we can find any number in one list and match it to a single counterpart in the other list. And here we have a nice rule that does that, right? Like 1 goes to 0, 2 goes to 1, 3 goes to -1, 4 goes to 2, 5 goes to -2, etc. We can continue this rule forever, and in fact, if we choose any number in, say, the right list, the list of integers, we can find a counterpart, we can find a match in the natural numbers. And in that way, we say that the natural numbers account for all of the integers, even though they're integers that are clearly not natural numbers, and therefore they're the same size, right? And if I just lost you, what I basically told you is that infinity plus infinity is infinity. Right, your 8-year-old is gonna love that. That's how little kids talk, right? And because that's so cool, I'm going to play a little riff on the saxophone. So this gets even better. If I were to dump all of the fractions into my existing set, I get a new set that mathematicians call the rational numbers and denote with this special Q. And it turns out that the size of the rational numbers is also aleph null. This is absurd, of course, you're thinking to yourself. There are an infinite number of fractions just between 0 and 1, 1/2, 1/3, 1/4, 1/5, etc. Surely this must be a larger size. This must be a set of a larger size. Well, let's see if we can find a rule that associates all of my rational numbers to all of my natural numbers. If so, then they would in fact be the same size. Now we're talking about fractions, and fractions are really just one number on top of another, a numerator on top of a denominator. And so I'm going to write all my numerators horizontally and all my denominators vertically, and that's going to give me a grid. And in this grid, in each box, what I'm going to write is all of the fractions that they create. There are some redundancies, right? Some of them reduce. Don't worry about that. It doesn't cause us a problem. What we do want to do is we want to find a rule that associates all of these rationals to all of our natural numbers. And this rule has to do two things. First, it has to enumerate all of the rationals, right? We want to say which box is first, second, third, fourth, fifth, because that matches up with our natural numbers, 1, 2, 3. The other thing we need to do is we need to make sure that we cover every number in the grid. We have to get everything. We can't leave anything out. So how do we do this? Oh, I know. Draw a counting snake. All right. So here's a counting snake. It's clear that if you were to let this counting snake go forever on this grid, we would cover the whole grid, and we can enumerate the boxes in the order that the counting snake eats them. So, all right. So in that way, we can say that once again, the natural numbers account for all of the rational numbers. Now, if I just lost you again, what I basically just told you is that infinity times infinity is infinity. Your 8-year-old is going to love this because that's how little kids talk, and that's also cool, so I'm going to play another blues riff. Now, you may be asking yourself, well, is there a larger infinity? Is everything just kind of aleph null? And it turns out that there is. The real numbers consist of everything we've talked about thus far, plus another set of numbers called the irrational numbers, which are characterized by having an infinite number of non-repeating decimal places. In case that sounded confusing, you know some of these irrational numbers like the square root of 2 or pi, right? And it turns out that the size of is in fact larger than the size of the natural numbers. Well, how is that? What do you mean a larger infinity? That seems like a very uncomfortable concept. Well, remember that this whole project is associating lists, and it turns out that if we generate any list of natural numbers and associate them to any list of real numbers, we can find and we can construct a number that on the list but is part of the set of real numbers. And that was confusing to say and hard to remember, so I'm just going to do it with you right now. Let's first pull up our lists. We have the natural numbers and we have the real numbers. The real numbers are selected such that they have an infinite number of non-repeating decimal places as indicated by the ellipses at the end of each number. And they also consist of all zeros and ones. Surely this doesn't cover the real numbers, I know, but it makes the trick that I'm about to show you really easy to explain. So observe the prestidigitation. In order to construct this excluded number, we go to the first number in our list. We go to the first number. We change it, right, from 1 to 0, and then we write that down as the first number in our excluded number. We then go to the second number in the list. We go to the second digit of the second number, change it, and write that changed number down as the second digit of our excluded number. And we can continue this process forever. Right? We are guaranteed that the number in red is excluded because for every number in the list of real numbers, in this infinite list of real numbers, it will disagree with our excluded number at some point. One digit somewhere is going to disagree at least because we've constructed it this way. And that means that this particular list of natural numbers does not account for the real numbers. But as I said before, we can carry out this process with any possible list of natural numbers and real numbers, which means that the natural numbers can't account for the real numbers at all in the same way that they accounted for our integers and our rational numbers. But the natural numbers are also an infinite size set, so that means that the real numbers must constitute a larger infinity. Now this gets even more fun. There's an argument by leading set theorist W.H. Wooden that says that the cardinality, oh, by the way, the cardinality of the real numbers we're going to call aleph 1, right? It went up from, and mathematicians sometimes call this infinity uncountable. Now there's W.H. Wooden, which says that this aleph 1 is actually just 2 to the power aleph null. But if we can do stuff like that, then what's to stop us from considering that there might be an aleph 2 that's 2 to the power aleph 1, or an aleph 3 that's 2 to the power aleph 2, and so on. And what we're drawn to is the conclusion that there are actually infinite infinities each. Now, this might be a little bit too intense for your 8-year-old, who is either crying or is a budding mathematician. And because that's pretty heavy, Liz and I are going to play some contemplative music. in case you didn't follow that whole infinity discussion completely, don't sit there trying to figure it out. Don't worry about the technicalities. What I want you to do is just get in touch with how it feels to learn that there are actually infinite infinities. How does it feel to know that when you contemplate the mysterious concept forever, you contemplate but an infinitely small measure of existence? That imagination is literally inconceivably vast. The first time I learned this fact, it felt a little bit like the first time I heard Petrushka by Igor Stravinsky or Rosewood by trumpeter Woody Shaw. I was awestruck that the human mind could conceive of such a thing, grateful that my life in its ups and downs had brought me to the point that I could experience it, and deeply desirous of sharing that feeling with others. So math and music connect in several places. The sciences of sound, signal processing, instrument design, and acoustics are all shaped by principles which are of course written in the language of mathematics. Ideas in rhythm and in Western harmony are cousin to certain ideas in number theory and topology, and sometimes there's even some direct cross-pollination. Fields medalist Manju Bhargava notes that what we now know as the Fibonacci sequence was actually discovered in medieval India as a result of exercises in rhythm and poetry. And mathematical physicist Stefan Alexander uses his studies in jazz saxophone to think outside the box on string theory equations. But the platitude that math is music rings hollow to me. While some working musicians are interested in these connections, by and large, the musicians that I've met are not particularly enamored of me and haven't relied on it heavily to hone their art or their craft. And conversely, many mathematicians are not exceptional musicians or even entertainers. Furthermore, the neuroscience on the math-music connection is inconclusive. We know that mathematics and music complex systems utilizing both hemispheres of the brain and are thought to lean heavily on language processing and spatial reasoning, but the full and true extent of the overlap is yet undiscovered. And even some of the more famous studies that link math and music don't quite live up to their place in our popular imagination. The Mozart effect, the idea that playing Mozart for school children will improve their math scores, is now thought to be a specific case of a larger effect called enjoyment arousal, which says that doing anything that puts you in a positive mood will help you improve on any number of tasks. It's not math and music specific. So let's review then. It looks like the link between bodies of musical and mathematical knowledge, but not particularly foundational in practice. Mathematicians and musicians lead starkly different lifestyles and talk about starkly different things, and the neuroscience is far from settled. It seems that unless we're to invoke poetry of the ancient Greeks and their ancient Egyptian pedagogical ancestors, we don't even have a mystical connection. And yet, in my experience, I see a profound connection in the texture of thought and the aesthetic quality of these two disparate worlds. I'm not alone. International jazz pianist and topologist Rob Schneiderman notes that mathematicians jam on problems in the way that musicians jam on tunes. And I would add that there is a personal as well as social dimension to this. For me, the connection is in the inspiration, the joy of learning the great ideas of those who came before me, the transformation of dots and squiggles on a page into pictures and sounds in my mind, ecstasy of solving a difficult mathematical puzzle or having a composition finally come together. There's a sense of majesty, of wonder, of aliveness, of beauty. But I think the problem is that the word beauty is not quite potent enough. And that's why it's often hard to see this particular connection between math and music. Develop good science questions around a concept with no obvious moving parts, and it's hard to develop good philosophy questions around an idea with no conceptual boundaries. Okay, so let's set some. By beauty, I don't mean inspiring of lust or care, nor do I mean inspiring of community or empathy in the way that many of these talks do, nor do I mean simply pleasing to the senses. The sensation I'm talking about has the following elements. It's life-affirming, paradigm-shifting, and humbling. It clears out the dust from everyday life. Earned. It has a sense of looking out from the top of some mountain that you almost died attempting to scale, or of meeting and mastering some dark part of the psyche, or of surviving a cold shower. There's a bittersweetness that adds crucial flavor to the bright, bursting joy, the experience of your own personal infinity. And I'm doing my best to evince this feeling in you right now with words, to reveal this emotional color and metaphor, because I don't know the word that does it. I have an idea. Thank you. So here's the opportunity. Princeton music psychologist Elizabeth Margulis denotes a relationship between practitioners, philosophers and theorists, and scientists in moving the field of music psychology forward. She says that practitioners can talk about a phenomenon as is lived. Philosophers and theorists can make generalizations based on these anecdotes, and scientists can tease out and test the relevant variables. As a practitioner, I hope that I can instantiate this math and music connection that kind of sloshes around in the cool sea cove of our collective unconscious. I hope that scientists can take my examples and work out the whole biology behind them. I hope that educators can teach it systematically and offer our children a healthy escape from the general malaise of life. I hope that leaders can make the beauty of this connection part of their daily ritual before they go out and make big decisions representing the people. But if none of this comes to pass, I hope that I've acted with a sense of the majesty and the wonder and the triumph of the connection between math and music. Thank you.